I think the problem is with my computer. Okay, we won't. It's okay. You're able to see? Oh, did I share screen? I think I have shared screen. You're able to see? Okay. So recall. So it's recording also, right? So let's see. I think it's recording. Yeah, it is recording. Okay, we have to edit that thing. Okay. So recall S of rho, right? Minus trace of rho log rho. What all did we show? We did a bunch of things, right? I'll just do. Suppose rho AB is U, then S of rho A equal to S of rho B. The proof is by the Schmidt decomposition. Then S of rho is the Shannon entropy of the vector of eigenvalues of rho. We did this, right? We did okay, so I don't recall all the things that we did. So we came to this, right? So we were doing one proposition. We did the Klein's inequality, right? We defined S of rho sigma. I think I defined as S or D. D. Klein's inequality. So I proved derived this as defined this as rho log rho minus rho log sigma, right? And D of rho sigma is greater than equal to 0. This is what we showed. So I will do a proposition. So suppose PK 1KK is a projective measurement. So what does it mean? PK equal to PK dagger equal to PK squared, and summation PK is I. Suppose I have this. Then if you don't tell me the outcome, this is the state of the system post measurement. And this is more uncertain than the system itself, the original system. If you do a measurement and you don't tell me the outcome, it's harder to predict the state in some sense. Okay, so you said there should be a way to prove, right? So I'll give you a proof, and the proof is slightly tricky, but at least there's only one. I think one thing that you have to maybe keep in mind. So whenever you're trying to prove inequalities of this kind, right? Just 1 second. I just want to see. Oh, there is there. Okay. Okay. If I want to prove inequalities of this kind, right? You use this thing. So S of, that's why I proved this in the beginning, the Klein's inequality. So S of rho sigma. So we know this, right? 0 is less than equal to S of, let me write it as alpha beta. So this is what? This is trace of alpha log alpha minus alpha log beta, which means this is trace of minus alpha log beta. I'm just writing the first term, the beginning, minus S, plus S of alpha, right? Minus S of alpha. Correct? So I want to show, so recall, I want to prove this, right? I know this is greater than equal to 0. So this implies what? This implies for any for any density operators alpha, beta, we have trace of minus trace of alpha log beta is greater than S of alpha, right? From here, this being greater than equal to 0 from this thing. So this gives us a clue how to what to choose alpha and beta, right? So remember, we want to show this. So let alpha equal to rho and beta equal to summation pk rho pk. Okay. So what do we have? We have minus trace of rho log. I'm going to write this in square brackets. Pk rho pk. This is greater than equal to S of rho, right? Because I've chosen alpha to be rho and beta to be that. Okay. So somehow I have to get this inequality, right? This is the desired inequality. This is the desired inequality. This is my desired inequality. So I observe. So there's a trick here. So rho log k pk rho pk, right? So I have an identity sitting here. So this is greater than S of rho. Yeah. So I know the identity is summation pk, right? Remember, I equal to summation pk or pj. This is also same as pj squared. I want to somehow get this also to have a pj, right? So what I do is, so that's what I said. I want a better proof, but this is really all that I know. Log of summation k pk rho pk. And here I'm going to write this red quantity. I'm going to write this identity. I'm going to write it as summation pj squared. Is that okay? Okay. Again, continue. So I can get the summation outside. So I can say j trace rho log k pk rho pk pj squared. All that I've done is got the summation outside. Okay. Cyclicity of the trace AB is trace BA. So I can say this is minus summation j trace. I can get one of the pj's on the left, pj rho, and then I have a log k pk rho pk pj, right? Now what? So log x and y, log x and y, right? So if x and y commute, does log x and log x and y commute? Suppose xy equal to yx, then is log x times y equal to y times log x? Remember, this is not, this is an operator, this is an operator. Okay. Because log x is, you have the same basis, right? So you're applying the log on the eigenvalues, but the spectral decomposition, the projectors in the spectral decomposition are identical, right? So if x is summation lambda I fi, y is summation fi, something, right? I mean mu j fj. So x and y commute, and log x is essentially summation log lambda I fi, right? So log x and y also commute. Okay. Okay. So that means, so if I look at these two terms, right? If I look at this term and this term, I have to only see whether summation pk, rho pk, and pj commute. Do these commute?
Yes.
Yeah. So note. Yeah. Note. So zero if j is not equal to k, right? And if k is equal to j, then I'm going to get pj rho pj, right? J equal to k. Similarly, you show that pj summation pk rho pk is also the same. It is 0 if j is not equal to k, and pj rho pj if j equal to k. Correct? Okay. So that means log of, so these two terms commute. So I have rather this quantity, copy, paste. So this thing is equal to paste the same thing, and I'm going to put the pj on the left and the log on the right. So then I have what I need, right? So then I can pull the j inside, the summation inside. So I have j pj rho pj log summation k pk rho pk, right? So this is exactly a minus with a minus. So this is exactly minus trace of what we want. This is your s of summation p k rho pk. And going back, we had this to be greater than equal to s of rho, right? This is what we started. We started with the left hand side. So we showed that this is greater than equal to s of rho. So we are done. Okay. Proof is very tricky. I wish I can get a better proof. So that means if you make a complete orthogonal measurement, the entropy increases. Okay. So recall in the classical world, right? I think you showed this, right? H of, if I have a bunch of random variables, h of x, y is less than equal to h of x plus h of y, right? So this is usually referred to as subadditivity. So what is subadditivity? You essentially have a function. So suppose you have a ground set 1 to k, and you have some function from that ground set. So let's say not this way. So suppose I take p. So let's call this omega. Let's take p of omega. So it's the subsets of it's the power set of omega. Okay. So I have a function f going from p of omega to r. Okay, so that means what? It takes every subset and throws out a number. It's a set function. It's a set map. Okay. F is subadditive if f of a union b is less than equal to f of a plus f of b for all a, b inside, or I'll just say all subsets of omega. Okay, you understand? You've come across subadditive function? Yeah, okay. Well, that's slightly different, right? Because you have x plus y, norm x plus y is less than norm x plus norm y. That's what you're saying. That's slightly different because there you can scale and there okay, okay, okay. So you're associating the norm of x plus y as the norm of x comma y, the set x comma y. That's a little strange. Probability is subadditive. Probability measures are subadditive. Okay, so this entropy function is subadditive. Okay, so so we'll prove the quantum analog of it. So S of proposition S of rho AB is less than equal to S of rho A plus S of rho B. This is just a lot of algebra, so I leave the last part of the algebra as a homework. So if you recall, how do you show x? I don't know how you showed h of x. I gave this in the homework, right? H of x plus h of y, right? And how you show it, I think you do this. You show the divergence between pxy and pxpy is greater than equal to 0, right? I think this is how you show, right? We'll do exactly the same thing, but the steps will be slightly more involved. So let's do that. So I know is 0 is greater than equal to less than or equal to S of rho AB, divergence rho A tensor rho B. Let's write down what this is. This is essentially minus trace of, sorry, there's no minus, rho AB log rho AB. Sorry. Minus rho AB log rho A tensor rho B. Right. So this is minus trace of rho AB log rho A tensor rho B minus S of rho AB, correct? So if I just show that suffices to prove that this minus trace of rho AB log rho A tensor rho B is S of rho A plus S of rho B, correct? Because then, I mean, essentially what I did in the in your what you did in the homework. So this, if I do that, then I will end up getting S of rho A plus S of rho B minus S of rho AB, and this being positive implies, non-negative implies that S of rho A plus S of rho B is greater than or equal to S of rho AB. Okay. So we just need to show this. This is a little bit of algebra, but we'll do a little bit of algebra, not too much of it. So rho A, so let's rho A equal to lambda I xi rho B mu j yj yj rho A tensor rho B. Let's do rho A, let's do log of rho A tensor rho B. So what is this? Log of, I mean, it's an operator. I should not be writing like this. So let's just do this. So I want to compute this. So let's just do rho A tensor rho B. Rho A tensor rho B. Well, maybe I'll do. Okay, so rho A tensor rho B is I j lambda I mu j xi outer product xi tensor yj outer product yj. Okay, log rho AB log rho A tensor rho B. This is I j log lambda I plus log mu j, because the log of product is the sum of the logs. This whole thing times xi tensor yj yj. Okay, so this is, okay, this is, I can write it like this, right? I j, I mean, if you look at it, it is actually this log lambda I xi tensor yj plus I have to copy paste the same thing. So I'll do this. How many of you use an iPad? None of you. Tejas does.
Yeah, I have.
This I find this notes to be very good actually. This note taking app. Okay. So this is what you get. So when you sum over j, right, you get I log lambda I xi tensor ib plus j log mu j ia tensor yj. Okay. So I end up getting something like this, right? Log rho AB log rho A tensor rho B is rho AB log rho A tensor IB plus rho AB log IA tensor rho B. So all that I've done is I've just so I log rho A tensor log of rho A tensor rho B. I ended up getting this. So I interpreted that as so it is, I mean, this is essentially lambda I log of this operator tensor IB, which is rho A tensor IB. That's all it. Okay. Okay. Now I will leave it from here to show. So this is homework. What I'll tell you how you do it also. Show that this is S of rho A and this is S of rho B. And the way you do it is take rho AB to be summation ij gamma ij and then you will see that gamma ij summation over j is lambda I and summation over I gamma ij is mu j, and you will use these relations to show this. Okay, so I will leave that last part. So use this, I mean, write it like this, and then you will use these two relations and you will show it. Just a little bit of a lot of algebra. So essentially it is the same sequence of steps, only that you have to do it in the operator sense. So I will just conclude that S of rho AB is less than equal to S of rho A plus S of rho B. But there are two interesting small corollaries out of this, which I will state. If I look at S of rho AB, I have an upper bound on S of rho AB. I'll give you a lower bound on S of rho AB. S of rho AB is at least the mod of S of rho A minus S of rho B, and it's a very cute proof. So I'm giving you a lower bound. The proof is very interesting, very cute proof. I mean, the book does it differently. One can just do it this way. So let rho AB, so take a reference. So let this be purified. Okay, I can always purify it, right? We know S of rho AR is less than equal to S of rho A plus S of rho R, correct, right? Subadditivity. What is S of rho R?
Same as S of row A,
S of rho
AB. Like last time we did that. Yeah.
Yeah. So because ABR, rho ABR is pure, each part has the same entropy. You take any cut, it'll give you the same entropy, right? So that means this is S of rho A plus S of rho AB. What is S of rho AR? Similarly, S of rho AR is S of rho B. So this is S of rho B. So S of rho AR is S of rho B. So this is equal to S of rho A plus S of rho AB, and we have got one part of the inequality. So what have we got? I mean, this is not equal to, this is equal to, this is equal to. So this implies that S of rho B minus S of rho A is less than equal to S of rho AB. Now what you do is you perform the same sequence with A and B flipped. Okay, so I'll copy this, copy, and I will paste it here. And what I'll do is I'll just so this is B, this is B, this is B, this is B. Now this becomes A, this is B, and you've got A and B swapped. Rho A minus S of rho B. So we have, so S of rho AB is greater than equal to both S of rho A minus S of rho B. Okay, because S of rho A B is greater than equal to both this way and that way. There's only one homework with the subadditivity. Okay. Recall we had one, recall this. So recall, this is one thing we did not recall as a recap. So suppose rho 1, rho 2 to rho k have orthogonal support. P1 to Pk are all non-negative. Summation Pk is 1. What is S of summation Pk rho k?
Sum of them, sum of pK S of rho K.
No, this is equal to, first you tell me the mixture, the entropy in the mixture, and then you tell me the average S of rho k. So the way you should think of it is the uncertainty in this mixture, right? First tell me what is your index. How many bits you need to tell me what is your index? You need so many bits. Once you tell me that, with that probability, you have to give me the entropy of that state. Okay, so that's the chain rule. So this is kind of, h of x plus h of y given x, because first you tell me x, then based on x you tell me what is h of y given x. What is this? This is px of x, h of y given x equal to x, right? So once you tell me, so with probability px, you will need so many bits. So the total number of bits is this. So this is exactly similar to this chain. This is what is called a chain rule. So first describe the bits to me, which is that index k. First describe the index k. For that you need so many Shannon bits, entropy bits. Once you describe that, if it is k, I mean, let's say little k, then you need S of rho k, and that occurs with probability pk. So you do, this is the average. Okay, so this we have, but this is when rho 1 to rho k have orthogonal support, right? What if rho 1 to rho k do not have orthogonal support? What can we say about this quantity? Okay, that's what we will talk about now, and this is concavity of entropy. For any PMF, P1 to Pk, and states rho 1 to rho k, not necessarily with orthogonal support. We have so if I look at this, S of concavity, right? Concavity means that if I take the mixture, concavity means this, right? So if I take the mixture and evaluate, that will be larger than the mixture of the evaluations. This is a mixture of the evaluations. So just for clarity, so suppose I have a function f. I have a function f. Okay, I take 2 points x1 and x2. Just telling you what is concave function. I can take f of x1, f of x2. I can mix the two with some ratios. This will be lambda f of x1 plus 1 minus lambda f of x2. So this is the mixture of the evaluations. Whereas on the other hand, I can mix the two arguments and then I can evaluate the function at that value. That is this. That is f of lambda x1 plus 1 minus lambda x2. Okay. So the function at the mixture point is larger than the mixture of the function points. Okay, some broad level. So that's exactly this. So entropy is concave. So when I mix rho 1 to rho k, the entropy I get is greater than pk s of rho k. Okay. And whatever you got previously when their orthogonal support happens to be the maximum you can get. So if you want to get maximum entropy, you need to have your rho k's to be orthogonal, other orthogonal support. Otherwise, you're only going to get lesser. So this is pk s of rho k. That's the statement. Is that okay? So there is a tight bound on this quantity. It's at least this and at most this. Okay. Yeah. See, if they are orthogonal support, right, then there is equality here. So there is equality here, right? If they are not orthogonal, the value of the entropy of the mixture is at most that. So that means it's going to be lesser than that. So because it is concave, yes. So if you are completely orthogonal, then you'll reach the maximum. But if your support is not orthogonal and they overlap, then the entropy is smaller than that value. So that is the best you can get if you want to maximize your uncertainty. Okay. Concavity is really here. Okay. One proof is actually straightforward. Not straightforward, but you can, if you have a little bit of experience, you'll get it. So A, I'll call this B. Okay. So proof of A. I want to show the following. Pk s of rho k is dominated by s of summation pk rho k. This is what I want to show. Okay. What I'll do, I'll say rho AB is summation pk ek tensor rho k, where E1 to ED are O and B. So what I'm doing is I'm orthogonalizing them by putting a tail in some sense. I'm attaching a tail to the rho k's and making them orthogonal. Okay. What is rho A? So we know clearly that S of rho AB. What is S of rho AB? S of rho AB is H of P plus summation PK S of this thing, right? But this thing is same as rho K, correct? This is what it is. See, the rho K's are not orthogonal to begin with, but I orthogonalize them by putting a tail to each one of them. That's orthogonal. So I define that as my rho AB mixture.
Just one question.
Uh-huh.
So the A system stands for the EKs and the B system stands for the rho K.
Correct.
Okay.
Yes. So this is this guy is the same as this guy, correct? Because you're just putting a tail, right? And the eigenvalues don't change. Clear? Srinidhi, clear? Okay, so where is your doubt? Tail. See, what am I doing? I am just tensoring it with orthogonal vectors. So think of this, okay? So I have two vectors, 0. So think of this, yeah. So let's say I have this and this. Okay, these are not orthogonal, right? What I do, I'm going to tail it with 0 and plus tensor with 1. Are these orthogonal? Let's look at this. So this is vector A, this is vector B. What is AB? AB is you will have 0 plus times 0, 1. So this will be 0. I'm giving a tail and making them orthogonal in some sense. I am defining my operators on orthogonal spaces. I am cooking up, but one component of it is what you started with. Yeah. So yeah, the part EK will make. So I'm defining new operators that are orthogonal, but whose components are coming from which were not orthogonal.
Like it is defining them acting independently on like some new k-dimensional
Yeah.
space.
Yeah.
Like yeah.
Yeah.
K times this. Like,
Yeah.
you updated k copies of your space and
Yeah. So it's a k-dimensional space. So the number of indices that dimensional space. Okay. So just to ensure that everything is okay. So this is my PK, EK tensor. Okay. I have kind of and I've mixed them also. Mix these guys. So S of rho AB, as we figured out, is H of P plus S of PK S of summation PK S of rho K. S, what is rho A? Rho A is PK EK outer product EK, right? What is S of rho A? EK is a lot orthogonal. So this is the Shannon entropy of the vector P. What is rho B? Rho B is PK. I'm tracing over the first component. So the outer product will become the inner product rho K. So this is summation PK rho K. And S of rho B is S of summation PK rho K. So what do we have? So we have H of P plus summation PK S of rho K. This was our rho AB, S of rho AB. And this we know is less than equal to S of rho A plus S of rho B, which is given by H of P plus S of Pk rho K. Okay. So by just defining the right operator and applying the subadditivity, I'm able to get this. So I end up getting summation Pk S of rho K to be less than S of summation Pk rho K. So here, the way I would think of it is I had actually one clear reasoning for this. Okay, I'll tell you the way to think of it. So start with rho K equal to pure states and try to prove, start with this, not necessarily orthogonal, and try to prove. Let me think, give me 1 second. Let me think. What is, I had a reasoning for actually doing this. See, okay, the way I see it is, you are in some sense going back to the classical. See, by making them orthogonal, you are in some sense going back to the classical. So the way you want to do this, okay, so if you look back at the proof of the following, right? Suppose I take a mixture of random variables, Pk, Xk, you can actually show that this is less than equal to, how is the concavity? So yeah, this is greater than equal to Pk H of Xk. And if you see what you're doing this, you're mimicking that by defining this rho AB. That's the way I see it. I'll give you a more clear explanation by writing the proof of this classical thing and comparing with the contrasting with the quantum. That's the way I see it. You're trying to somehow mimic the classical proof, so you make things orthogonal. That's the way I see it. But that's a good question. I'll give you some reasoning why this is the right way to prove it. Actually, in the second part, you will see that we take pure states and we kind of fight with it. Okay, so that is that. So B. So now to show, I want to do the following. S of summation Pk rho K is less than equal to H of P plus summation Pk S of rho K. Okay. Okay, here I will kind of do what I said. So suppose I take my rho K to be, say, Xk, but not necessarily orthogonal. If they are orthogonal, then there is equality. Remember, if there is orthogonal, there is equality there in the above. Okay. So rho K 1 to K. So I'll break the proof into two parts. Step 1, let's say step 1, pure states. So okay, again I'm going to do the same orthogonalization trick. Okay, so let E1 to Ek be orthonormal. Orthonormal. Define theta to be root Pj. I want to take a state. So I know summation pj squared is, summation squared of root pj is 1. So I'm going to orthogonalize them exactly like the way I did them. I'm going to attach a tail and make them orthogonal. Okay. So this is a popular proof technique. I need this, right? Okay. So now let us define, I'll not use this rho. Rho is too confusing. So I'll use sigma AB. Let sigma AB be this rank 1 projector, theta. What is sigma A? So what is this? This is I J root Pi Pj Xi Xj Ei Ej, right? What is sigma A? I have to trace over the second guy. But when I trace over the second guy, it will squish. Remember, E R E S is delta RS, not Xis. Okay. What is sigma A? Sigma A is summation, sorry, Pi Xi, outer product Xi, right? What is sigma B? Sigma P is not that simple, right? Because Xi, inner product Xi Xj is not delta Ij. So I will just write it as is. Ij root Pi Pj inner product Xj Xi Ei Ej. The tensor goes off because that squishes into a scalar. Okay. This is sigma B. What is S of sigma AB?
S of A plus S of B.
What is sigma AB?
Oh, that's just 0. So,
Yeah, sigma AB is 0, right?
Yeah.
Because it's rank 1. As eigenvalues 1 and 0, 0, 0, 0, right? So we know S of rho A, any cut of it has equal entropy. We know this, right? What is S of rho A?
H of P.
This is actually, if you look at it, what is, can I say this is this Pi rho I? Because that's my rho I, right? Remember, it's a pure state. I've taken a pure state case. So S of rho A is this. S of rho A is this. Huh? Okay, look at sigma B. Sorry, I should not, I made a mistake here. I should say sigma. That's why I think you're silent. Sigma. 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 Okay. Look at sigma B. What is sigma B? Sigma B is this weird guy, right? I J root Pi Pj Xj Xi Ei Ej, right? What do I want to show? Remember, I want to show the following. I want to show S of, I want to show the following, right? S of Pi rho I is less than equal to H of P plus summation Pi S of rho I, right? This is what I want to show. Correct? But what is the rho i's? Rho i's are all rank 1 operators. So this quantity is actually 0. Right? So I have got this term. I want to show it is less than this term. Okay, so the way is the following. Look at this. Suppose I make a projection measurement on sigma b. I make a projective measurement on sigma b. So this is my PL, 1L, K, whatever that is. What do I know? I know S of sigma b is less than equal to S of summation PL sigma b PL, correct? This is by the complete orthonormal measurement. I think we proved today. Huh? EL. So when I make, what is summation PL sigma b PL? That would be exactly the following. PL, EL. Because when I hit this with EL and EL, then I equal to L, I equal to J equal to L. So S of sigma b is less than equal to S of summation PL sigma b PL, but this is S of summation PL EL, which is H of P. And here this, by the cut, I know this is S of sigma A, but this was what I wanted. That is S of summation PL rho L. So summation S of summation PL rho L is less than equal to H of P. I only put it for the pure state. Okay, I think given the time, I'll do the general thing. General is actually very simple. You just do the same thing, but you just take your rho L to be summation lambda L some XL T or something and show it. Just a generalization of this proof. It's actually not too hard, but I'll do it. This is actually the second last element in the quantum entropy. After that, we'll just do strong subadditivity. Just one theorem which I'm not going to prove. It's a very complicated proof. And then we'll go into quantum typicality. And then coding. Okay. Coding means Schumacher compression. CQ channel coding. We'll go to that, and there you will see all these entropy terms coming. So the reason, so one of the things we showed here was S of summation PL rho L is greater than equal to PL S of rho L, right? So we'll see in one of the important theorems, we will see that the rate is actually the difference between the two. So we'll see that it is positive, non-negative. This is just like your I of xy. H of y minus h of y given x. This is h of, the first term is h of y, the second term is h of y given. So just two things in the quantum entropy. One is strong, complete this proof, complete this for mixed states. And then we do strong subadditivity. There are some more things in Nielsen and Chuang, not Nielsen and Chuang, in Wild, which I will possibly do it at a later point. We don't need that right away. After this, I'll go into quantum typicality. And then I will do, okay, then I have to do, I can actually do next Schumacher compression. Or I can do packing and covering. Packing and covering. And then we will go into Olevo, Schumacher, Westmoreland theorem. This is kind of the broad. This is chapter 20. This is chapter 18. I think this is 15, 16. I think I might be wrong. This is 11 or 14 or something on that. Okay. You wanted algorithms, right? Your exam is tomorrow. It's the last exam. We can try and do later after tomorrow, after your exam. We can try. I'll let you know.
I mean, like, will you just be like privately telling them?
He wanted to learn the algorithms, quantum algorithms.
Yeah.
So he
How
said,
am I just sitting in?
"Oh yeah, sure, yeah, totally." Again, it's very. I too don't like the algorithms. I like something more
Yeah.
conceptual. But yeah, let me.
If you're talking to anyone, they'll ask you, like, you know, this.
What's this? Stop.